In this video, I kind of want to do something different than I normally do. I normally just solve a bunch of math problems, but in this video I actually want to explain some of the background information that we need regarding radical equations, since there is a lot of stuff to know. Let's go through our basic notation here. If we see a statement like this is the radical sign. This little n here, this is actually what we call the index of the radical. If you don't see a number next to the radical, we always assume that it's just a square root. We assume that index is the number 2. Whatever falls underneath your radical or inside the radical, that's what's called the radicand. I'm going to be referring to that later on in the video, so it's important we do get the vocabulary down. If we have this radical equal to a number, I'm just going to call this the result. So let's remember a few basic things about radicals. Taking a radical or taking a root is the inverse of raising to a power. So it makes sense that in order to solve radical equations, we will have to raise to a power to cancel out the root, the radical. By the way, root and radical are kind of interchangeable. They're synonymous. They mean the same thing. Given this general identity right here, this can actually be reinterpreted, rewritten as a raised to the nth power is equal to your radicand, or x. So when you take roots, we really just need to ask ourselves, well, what number do I need to raise to this n power in order to achieve the radicand? So you can think of some examples pretty easily. The square root, there's no index, square root of 64. When I ask the question, what is the square root of 64, I'm asking, what number do I need to multiply by itself, or what number do I need to raise to the second power to give me 64? The result, the answer is 8. And it's only positive 8 since we're only going to deal with what's called the principal square root function. And we'll see why in just a moment. But we call it the principal square root if we're just looking at the positive answer, not positive or negative. In reality, there are two solutions to the square root of 64. When we look at radical equations, we only pay attention to the positive results, though. We ignore the negative results. To view another example, we could say, what's the cube root of 8? What that's asking is, what number, if you multiply it 3 times over, or if you raise it to the third power, gives you 8 as a result? And the answer is a positive 2. And you can see why that's the answer. If you take 2, raise it to the third power, that's the same as saying 2 times 2 times 2, which is the same as 8. Because we can just simply do the math in reverse, we know that is the solution for the cube root of 8. In algebra, what we like to do sometimes is study what are called functions. And when we're looking at the square root of the cube root function, we're basically just matching up every number with its square root, or with its cube root, and plotting all those results on an xy coordinate grid. It's important to note that we are studying what's called the principal square root function. That means every number only has a positive square root, not a negative. The square root of 4, in this case, is positive 2, not negative 2. Now, why do we use principal square root function? Because if you looked at all the results, you say the square root of 4 is positive 2 or negative 2, then we would get something that is not a function. That would break what's normally known as the vertical line test. We were to graph out the negative part as well. So we're only going to look at the positive results. The domain of your principal square root function is only positive numbers. You can write it as an interval as everything from 0, including 0, to infinity. And as you can see, the range, or the possible output or y values here along the y-axis, is also non-negative numbers. So I think I said positive earlier. I didn't mean positive because we are including 0. And 0 is not positive or negative. But non-negative numbers are your domain and range for your principal square root function. That's important when we're dealing with solving equations, and I'll talk about that in just a sec. It turns out the domain and range for every even-powered root or even-powered radical fourth roots, sixth roots, eighth roots, all have the same domain and range, from 0 to infinity. When we look at odd-powered roots, if we look at the cube root function, for example, if my radicand is negative, it turns out my result is going to be negative as well. And that's true for all odd-powered functions. So the domain and range for any odd-powered radical function, the domain and the range are both the same. They are all real numbers. There's no what we call restriction on the domain or range. Again, that symbol just means all real numbers, or pretty much any number you can think about as long as it's not imaginary. So we are dealing with fractions, decimals, negatives, positives, zero, as long as it's not an imaginary or complex number. And by the way, when we deal with the square root or any even-powered root function, we're studying this as a function of a real variable, so we're going to ignore all imaginary solutions. We're not going to take the square root of the negative, and we're not going to look at the negative results. Okay, so because of what we know about the domain and range of even and odd root functions, there are a few things we need to keep in mind when we're solving either even root or odd root equations. To remind you, when I'm talking about even roots, I mean about square roots, fourth roots, or any root which has an even number as the index. So what we know about these is we have a restriction on both the domain and range. What that means is that for the domain, what's underneath the radical, what we call the radicand normally, the restricted domain tells me that the radicand cannot take a negative value. If we ever end up with a result and the radicand is negative, we know that that's a false result. And then we call those extraneous solutions. Another thing we know about even roots is that there's a range restriction. There's only non-negative numbers for your range. And so the results are what's on the other side of the equal sign. But if you have your radical isolated, the result also cannot be a negative. If either one of these is the case, we jump to a conclusion that this equation has no solutions, or it actually has what's called extraneous solutions. These types of equations may have these extraneous solutions. So we need to be careful with these. We need to be checking our work. Plug the numbers back into the original equation, make sure that they work. Okay, for odd roots, such as cube roots, fifth roots, and all that, there are no restrictions on the domain and range. Domain and range are all real numbers. That brings us to an interesting conclusion. When we take the cube root or the fifth root, where we can get a negative result, it turns out that if the radicand is negative, the result is negative. If the radicand is positive, the result is also positive. So there's no room for extraneous solutions. You should always practice plugging your answers back in, but we do know that when we take odd roots, we can deal with negative values. Don't really need to worry about extraneous solutions. Okay, so here's our basic rules for solving any kind of radical equations. Any equation that has a square root or a cube root or any kind of root in it. I suggest at this point pausing the video, writing down the important points, but actually I'm going to highlight the important points as we go along. First thing I was going to do is I'm going to isolate the radical, meaning if there's anything going on in the equation around the radical, we want to cancel that out by using the inverse operation. So we have to cancel out addition and subtraction before we can cancel out multiplication and division, based on the order of operations. The second step is we cancel the radical by raising it to a power. Remember, we are raising both sides of the equation to that power. Whatever your index was, or whatever nth root you're taking, you have to raise to that same power. We should now have an equation that involves the radicand. If there's anything besides just the variable, we continue solving it until we reach simply the variable isolated. And then we've solved the equation. We have to go back and check our work every time. So, you know what? Let me add that as a rule. Check your work. Check solutions. Some may be extraneous, and I will show you some examples of that.